So now we have all the elements in order to state and prove the geometric Hanh-Banach theorems. So remember, X, it's a linear space over the real numbers. And we'll start with the definition of an hyperplane. So let's assume that we have L, which is a linear functional, and different from which is not equal to 0. So L of x is not equal to 0 for all x. L is defined on the old set x. And so the sets of points x in x such that L of x equal to C, so if are called hyperplanes. So the hyperplane depends on two parameters, this linear functional and this constant C. So a set will be called an hyperplane if there exists a linear functional and a constant C such that it is equal to all points in x for which L of x is equal to C. So this is an hyperplane. And now I have the definition of half spaces. So the half spaces will be the sets of x in x such that L of x is smaller than a constant C, or all points x in x such that L of x is larger than C. So these are called half spaces. So a subset of x is called a half space if there exists a linear functional L which is not equal to 0 and a constant C for which the set coincides with the points x such that L of x is larger than C, or L of x is strictly smaller than C, or strictly larger than C. And closed half spaces are the same ones in which we replace this strict inequality by weak inequality, which means that all points x such that L of x is less or equal than C, or larger or equal than C. So these are the definitions of hyperplane, half spaces, and closed half spaces. So I can now state the first main theorem. It states the following. Let's assume that you have K, a convex set. Of a linear space X. Assume that all points of X of K are interior points. So all points X in K are interior. Then I am assuming that, well, K is non-trivial in the sense that K is non-empty, and that K is not the whole set, so there exists Y which does not belong to K. So you have a convex set, and you have a point Y which does not belong to the set K. And what I claim, then there exists a linear function L from X to R. So this is a linear functional. And there exists a constant C in R such that, well, K is contained in the set of points X in X such that L of X is smaller than this constant, and L of Y is equal to this constant. So this means that if you define the hyperplane as all points Z such that L of Z is equal to C, so there is here an hyperplane which contains Y. So this hyperplane and the convex set K will be contained in the points X for which Lx is strictly smaller than C. So this is the theorem I want to prove now. And, well, the proof will be based on these construction of the gauge function. So let me start the proof. K, it's non-empty, so it has a point. I call that point the origin. So let me assume without loss of generality that the origin belongs to this convex set K. So I have a point and I have a convex set K. So I can define P to be the gauge function associated to these two parameters. So just remember that P of Z will be the infimum over all A positive, such that 0 plus 1 over A times Z belongs to K. And we have proven that if you take a point X in K, well, by assumption, X is an interior point. And this implies that P of X, it's strictly less than 1. This is one of the lemmas we proved in the previous lecture. Now, let me take Y. So Y is this point which doesn't belong to K. Y doesn't belong to K. So this means that if I take A equal to 1, 1 doesn't belong to this set. One doesn't belong to the set A's such that 1 over A Y belongs to K. And remember that we have seen that this set, it's a semi-infinite interval. So we know that Y, so 1 doesn't belong. So this set, which is a semi-infinite interval, in the worst case, it can be the open interval 1 plus infinity, and this means that, well, P of Y is the infimum of this set. P of Y has to be larger or equal than 1, right? Because we have seen that this set, it's a semi-infinite interval. 1 doesn't belong, so it can be either open or closed semi-infinite intervals. So in the worst case, it will be the open interval 1 plus infinity, and therefore P of Y would be greater or equal than 1. So these are the consequences of our assumptions. And now, well, let's start constructing this linear functional from these properties. And, well, what we will do, we'll start, you have Y. Well, let's consider the state, well, the linear subspace Y, which is the linear subspace generated by this point Y. So these are all the alpha Y, such that alpha is a real number. So we have here a linear space Y, and we will define a linear functional on Y. And to define this linear functional Y, all elements of this set Y can be written as alpha Y. So by linearity, we want L to be linear. So the only thing I need to fix is the value of Ly. And, well, the value we will pick, it's the value, say, P of Y, which is larger than 1. So I'm setting L of Y to be P of Y. This is larger than 1. And therefore, L of alpha Y, it's equal to alpha L of Y for all alpha in R. And now, what I claim, and to prove that, maybe let me erase maybe well, the thesis. What I claim is that L is less or equal than P on Y. And these are the conditions which allow me to extend a linear functional. Remember, P being the gauge function associated to a convex set, we have seen this gauge function, it's subadditive and positive homogeneous. So if we have a linear functional defined on a linear space Y, which is bounded by this function P, we can extend L to the whole space in such a way that we keep this inequality. So I just need to check that indeed on the linear subspace Y, we have that L is bounded by P of Y. So, well, let me take alpha. So what we have to show is that L alpha Y, it's bounded by P alpha Y. These for all alpha in R. Well, let's first consider the case in which alpha is equal to 0. In this case, well, we have 0 on both sides. L of 0 is 0. And P of 0, well, P it's always non-negative. So this inequality is satisfied if alpha is equal to 0. Now let's take a positive alpha. In this case, L of, by linearity, L of alpha Y is equal to alpha Ly. And since P is positive homogeneous, this is equal to alpha P of Y. And L of Y has been defined as P of Y. So actually, these two quantities are equal, and therefore, well, that's fine. The inequality is satisfied. So let's consider the third case, which is alpha negative. Well, in that case, alpha L of Y, well, L of alpha Y by linearity is equal to alpha L of Y. L of Y, it's positive, alpha, it's negative. So this is, well, strictly less than 0. And P alpha Y, it's non-negative because, well, P by definition, it's non-negative. So this inequality, it's also satisfied if alpha is negative. So I just proved that L is bounded by P on Y. And now I can use the Hanh-Banach theorem. Right? I have a linear functional defined on a linear subspace. This linear functional is bounded by a function which is positive homogeneous and subadditive. Therefore, the Hanh-Banach theorem tells me that there exists a linear function L which is defined on the whole space. It's an extension. So L of Y it's equal to L of Y, and this is P of Y. And on the other hand, L of X it's less or equal than P of X for all X in X. So this inequality extends to all set X. But that's fine. So here I have the linear function I wanted. L of Y it's equal to P of Y. Now what remains to be done is to show that if X belongs to K, then L of X it's bounded by P of Y. Right? What we wanted, it's that will be my constant C. C will be P of Y. I have indeed that L of Y it's equal to that constant C. So to complete the proof of the theorem, I have to show that all points X in K are such that L of X it's bounded by P of Y. Well, but I know that L of X it's less or equal than P of X. So fix a point X in K. by this property, I know that L of x is bounded by P of x. Since x is an interior point, I know that P of x is smaller than 1. And 1, it's less or equal than P of y. So, indeed, all points x in my convex set K are such that L of x is strictly smaller than my constant C. So, I obtained a linear function L for which and a constant C, such that L of y is equal to C, and for all x in K, L of x is strictly bounded by C. And this completes the proof of the theorem. So let me state a corollary of this theorem. Again, I have K a convex set. But now I'm not assuming that all points are interior, but I'm assuming that there exists a point x in K, which is an interior point. And that, well, K it's a proper subset, so there exists a y which does not belong to K. And now the claim is that there exists a linear functional L from x to R and a constant C in R such that L of y is equal to C. And now instead of having the strict inequality, what we want to prove is that K is contained in the set of points, let's say Z in X, such that L of Z is less or equal than constant C. Well, and the proof it's exactly the same one. So you just, well, you have this point X. Let's say that X is equal to the origin, which is the element of K. This is an interior point. So since this point it's an interior, you can define P, the gauge function associated to this convex and to this point. Now, well, we know that if a point Z belongs to K, P of Z it's less or equal than 1. Right? Before, we knew that all points were interior points from which we obtained the inequality, the strict inequality. Now, we use one of the lemma we proved in the previous lecture, which guarantee that if you have a point Z in the convex set K, then P of Z is less or equal than 1. You repeat the same construction with your linear functional, and at the end, remember you have that K. In the previous proof, what you obtained is that K is contained in the set of points Z in X, such that L of Z it's less or equal than P of Z, which is less or equal than P of Y. We don't have, so remember before we had P of Z less than 1, which was less or equal than L of Y. Now you don't have the strict inequality, but just the weak inequality, and so you will get that, and this was the constant C, so you'll get that L of Z, which is bounded by P of Z by the construction of this linear functional. It will be bounded by P of Z, which is bounded by 1, which is bounded by C, which is the constant, which is L of Y. So the previous proof, the same proof, provides you this statement, which is now weaker because, well, you have only here a half hyperplane, and here a closed half space. You don't have anymore that K is contained in the half space, but only in the closed half space. Here is the second main theorem of this lecture. Now we have two convex sets, K1 and K2 are convex sets. They are both non-empty. Let's say that K1 has an interior point, so there exists X, which is in K1, which is an interior point. And K1 intersection K2 is empty. So we have two convex sets which are disjoint. And what we want to do is to construct an hyperplane which separate these two convex sets. So we want to show that there exists a linear function L from X to R and a constant C in R such that for all X in K1 and all Y in K2, L of X it's less or equal than C, which is less or equal than L of Y. So we can separate these two convex sets by an hyperplane. So the hyperplane of all points Z such that LZ is equal to C. So one of the convex sets will be in one half space, closed half space, and the other in the other half space. So this is what I want to prove. I need some space, so well, at some point I will have to erase the statement in order to prove this result. But let's start the proof. And so remember that K1 minus K2 is the set of all points which can be written as the difference of 2 points in each set. So these are all points X minus Y, such that X belongs to K1 and Y belongs to K2. And what I claim is that this set, let me call it K, it's a convex set. Well, that's very easy to prove. So let me take Z1 and Z2 in K1 minus K2 in K, and theta in 0, 1. And we want to prove that theta Z1 plus 1 minus theta Z2 belongs to K. So let's prove that. Since Z1 belongs to K, Z1 it's equal to X1 minus Y1, where X1 it's in K1 and Y1 it's in K2. In the same way, Z2 it's equal to X2 minus Y2. X2 belongs to K1, Y2 belongs to K2. Now, if I write theta Z1 plus 1 minus theta Z2, this is equal to theta Z1, it's X1 minus Y1. So let me just look at the first term. So this is theta X1 plus 1 minus theta. In Z2 I have X2. And this is minus, I have theta, in theta Z1 I have theta Y1 with a minus. And in 1 minus theta Z2 I have 1 minus theta Y2. Now you see that the set K1, it's a convex set. X1 and X2 are in K1. So this point belongs to K1. For the same reason, this point belongs to K2. And therefore, this subtraction belongs to K1 minus K2, which means that indeed theta Z1 plus 1 minus theta Z2 belongs to k1 minus k2, which proves that K is a convex set. So that's the first claim. Now, I claim that, well, you know that X belongs to K1, it's an interior point. So what I claim is take Y in K2, any point Y in K2, I claim that X minus Y is an interior point. Of K. So we just proved that K is a convex set. Now here's a point which belongs to this convex set K, X minus Y, because X is in K1 and Y in K2. I claim this point is an interior point. So to prove that it's an interior point, I have to fix Z in X and to show that there exists epsilon positive such that X minus Y plus TZ belongs to K1 minus K2 for all T whose absolute value is bounded by epsilon. Fine. So fix Z in X. Since X is an interior point, I know that there exists epsilon positive such that X plus TZ belongs to K1 if T is less or equal than epsilon. But then X plus TZ minus Y belongs to K1 minus K2 because X plus TZ belongs to K1 and Y belongs to K2. And this proves that for all T whose absolute value is bounded by epsilon, X minus Y plus TZ indeed belongs to K1 minus K2, which proves that all these points, X minus Y, are interior point, provided K is an interior point. So this is the second statement of this theorem. Now, my third claim is that the origin does not belong to K. So I have here a convex set K. I've seen that it has interior points. X minus Y is an interior point. And now I'm claiming that, well, there's a point which doesn't belong to K, which is K1 minus K2. Well, and this follows from the fact that the intersection of these 2 points is empty. Because, well, if 0 belongs to K, which is K1 minus K2, this means that there exists X in K, or maybe let's call it Z, because X I used already, Z in K1, Y in K2, such that 0 is equal to Z minus Y. But this implies that Y is equal to Z, and therefore we have a point Y, which belongs to K2 and to K1, because it is equal to Z. So that implies that K1 has an intersection with K2, but by assumption it doesn't. So 0 doesn't belong to K. So here are the assumptions. K1, K2 are convex sets. K1 and K2 are non-empty. The intersection is empty, and there is one interior point in K1. And what we proved up to now, that, well, if I take the difference, K1 minus K2, I call that K. This is a convex set. Whatever Y in K2, X, which is the interior point of K1, X minus Y2, Y, sorry, is an interior point of K. And finally, that the origin doesn't belong to K. Now, I can apply to the corollary to this set K, right? K, it's a convex set. The origin doesn't belong to K. K has an interior point. So all assumptions are satisfied. And therefore, the corollary tells me that there exists a linear functional L from X to R, such that K it's contained and there exists C, such that K is contained in the point Z, such that L of Z it's less or equal than C, and L of, well, the origin, it's equal to C. Right? So this is what the previous corollary was telling us. If, well, we have this point Y, which is in this case the origin which doesn't belong, we can always find a linear functional and a constant C for which K it's contained in the half space and 0 in the hyperplane. Of course, since L is linear, L of 0 is equal to 0, so that implies that in this case C it's equal to 0. In that, that constant has to be equal to 0. Since that constant has to be equal to 0, this means that this constant is 0, which means that K1 minus K2, which is my convex set K, it's contained in the set Z such that L of Z is less or equal than 0. But all points of K1 minus K2 are written as x minus y for x, or z minus y for z in K1, y in K2. This means that for all z in K1 and for all y in K2, we have that L of z minus y, it's less or equal than 0. Well, but this is the same thing because L is linear as saying that Lz it's less or equal than L of y for all z in K1, all y in K2. Now you define C0 as the supremum of Lz for z in K1. This supremum it's clearly finite because L of z, you take one element in K2. You know that Lz it's bounded by this Ly, call it y0, fix that y0. You know that Lz it's bounded by Ly0 for all z in K1, so the supremum it's finite. And therefore, what you get is that Lz it's bounded by this constant C0. And since Ly, you fix a y, it's larger than Lz for all z in K1, it's also larger than the supremum, so L of y, it's larger than the supremum, which is C of 0, for all y in Z2. In K2, sorry. So you know that by fixing the constant C0 as the supremum of Lz for z in K1, you get a constant C0 such that, well, L of z is bounded by C0 for all z in K1 because C0 is the supremum, and L of y it's larger than C0 for all y in K2 because, well, L of y it's larger than Lz for any z in K1, so it's also larger than the supremum, which is C0. And this is exactly what we wanted to prove. So we obtained a linear function of L and a constant z, 0, such that L of x is bounded by C, which is bounded by L of y. So we obtained an hyperplane which separates the two convex sets. So let me complete this lecture with two applications. One which is obvious and which will be used many, many times. Suppose that you have X, a linear space, which is normed, so normed linear space. And now you have Y, which is a sublinear space. And assume that you have a functional L, which is defined in Y, taking values in R, and such that there exists a constant C0 such that L of y it's bounded by C0 times the norm of y for all y in Y. So this tells you that, well, this linear functional, well, it's in some sense bounded on the set, on the sublinear space Y. And what I claim is that then there exists an extension L to X which satisfy the same bound. So there exists L from X to R, which is an extension, such that L of Y it's equal to L of Y for all Y in Y, and such that L of X it's bounded by the constant C0 times the norm of X for all X in X. Right? This is what I claim, and this is a simple consequence of the Hanh-Banach theorem, because, well, the norm, or a constant times the norm, this defines a function which is subadditive by the triangle inequality, and it's positive homogeneous by the definition of the norm. So you have that defined P by this expression. You have a function which is positive homogeneous and subadditive. Now you can, so L of Y, it's of course bounded by P of Y. You can apply the Hanh-Banach theorem, which tells you that you have a functional L, which coincides with small l on the set Y, and which is still bounded by P on the whole set, but P by definition is C0 times the norm of X. So that inequality holds. So if you want, any bounded linear functional defined on a linear subspace can be extended to the whole space to a bounded linear functional which is bounded by the same constant C0. By the way, something, well, which I didn't say and I should have said, is that, of course, this extension is not unique, right? If you remember the way in which we define the extension, we define it dimension by adding some new linearly independent points. We had defined A, and in the way in which A was defined, well, A needed to satisfy certain bounds. So if these bounds were not strict, we had liberty in order to prove some freedom in order to choose these point A. So this extension, it's very easy to find examples. These extensions are not unique. So Hanh-Banach just tells you that, well, there exists an extension, and here I'm saying, and keep in mind that, well, these extensions are not unique. There are many examples in which you have more than, well, a family of possible extensions. So here is a second application, and for that, I will assume that I have a space omega, which is an abstract set. And I will represent by B of omega the space of all functions x from omega to R, such that, well, the supremum in omega of x of omega, that this is bounded. So it's clear that B of omega, it's a linear space. You can add two functions, and you can multiply a function by a scalar. And, well, I'll say that a function, it's non-negative if x of t, it's larger than 0 for all t in omega. And that introduces a partial order. I can say that x, it's less or equal than y. Well, if x of t, it's less or equal than y of t for all t in omega. Right? Now, let me consider a linear functional. So let's say that L, it's a linear functional from B omega, or a subset of B omega. Let's say that subset Y of B omega to R. I will say that it's positive if L of x it's larger than 0 for all x larger than 0. Okay, so I defined that x it's larger than 0 if f of xt it's larger or equal than 0 for all t. Now I'll say that linear functional defined on subspace of the set B of omega, it's positive if L of x is non-negative for all x larger or equal than 0. So just remark, if I have that L which is positive, and I have x1 less or equal than x2, and L is linear, of course, linear, then L of x1 it's less or equal than L of x2, right? Because, well, x1 it's less than x2, so this means that x2 minus x1 it's non-negative, therefore L of x2 minus x1 it's non-negative, and by linearity you get this inequality, which means that if you have a linear functional which is positive, it's also monotone in this sense, that if x1 it's less than x2, then L of x1 it's less or equal than L of x2. And what I want to prove is the following theorem, which is an extension theorem. You have Y a linear subspace of Bs, B omega, so it's a linear subspace. I have L defined on Y, which is linear and positive. And I will assume that Y contains, so there exists a Y0 in Y, such that Y0 is strictly bounded by some constant C0, which is strictly positive. Okay. Well, if I take Y0 divided by C0, by linearity, this, since Y it's a linear subspace, this is also an element of Y. This one it's bounded by 1, so without loss of generality, I can assume that there exists Y in Y0 in Y, such that Y0 it's strictly it's bounded below by 1. And what I want to prove is that, well, I can extend L to the whole space. So there exists L, which is defined in the whole space. Which is an extension for all Y in Y, and also that L it's positive, so that this function it's positive, which means that if you take x non-negative, then L of x it's larger or equal than 0. So I want to prove this theorem. And for that, well, I need to define a positive, well, proof it's based in Hanh-Banach. Hanh-Banach relies on a function which is positive homogeneous and subadditive, so I have to define, and this is the main idea in the proof of this theorem, how to define P. So here is the definition of P. Take x. I want to define P of x as the infimum of L of y for all y such that x it's less or equal than y in y. Right, so you take all functions y, in this your linear subspace. L of y it's defined on this subspace, so this is well defined. You take all those ones which are bounded below by x, and you take the infimum of these values, you define that as P of x. My first claim, my first observation is that P is well defined. So P of x, well, it's not plus infinity and it's not minus infinity, so P of x belongs to R for all x. Why is that so? Well, x, it's an element of B on omega, so this means that x of t, it's bounded by some constant C, right? The space B, it's the space of all functions which are bounded, so there exists a C for which xt, it's bounded by C. So since y0, it's an element of y which is strictly larger than 1, this means that x, it's bounded by this constant C times y, 0, right? Because x, it's bounded by C, y, it's larger than 1, and it's also bounded below by minus C times y0, right? These two inequality hold. Now, let's take a function y. So let me show that this infimum, it's finite. Well, this infimum, so P of x, it's an infimum. Well, this function C times y0 belongs to the linear space y, so it belongs to this set. So P of x, it's bounded by C L of C y0, which is equal to C L of y0, and this is finite, right? Because, well, L, it's a linear function, it's defined on this space. So on the one hand, from the fact that C, it's bounded below by C times y0, we have that Px, it's bounded by this value, therefore Px cannot be equal to plus infinity. Now let me show that Px cannot be equal to minus infinity. So take your y such that y, it's larger than x, but x, it's larger than minus C times y0. This means that y, it's larger than minus C y0. L, it's positive, therefore monotone. This means that L of y, it's larger than L of minus C y0, but this by linearity, it's equal to minus C L of y0. And this proves, therefore, that whatever y in this set, in y such that y is larger than x, L of y is bounded below by minus C times L of y0, and therefore P of x should be larger than that. So we have two bounds, a lower bound and an upper bound for P of x in terms of this function y0. All Px, for all x, Px, it's bounded above by C times L0, L of y0, and bounded below by minus C times L of y0. So this is the first observation. So here's what we are trying to prove. We have y a linear subspace. I'm assuming that this linear subspace has an element y0 which is bounded below by 1. We have a functional L defined on y which is positive and linear, and we want to extend it to a linear function defined on the whole space which is also positive and linear. Up to now, I defined Px, which is given by this formula, so it's the infimum over all Ly for all y in y larger than x. And what we proved is that if xt, it's in absolute value bounded by a constant c, then P of x, it's bounded below and above by these quantities. Now my claim is that, well, this function P, which is defined in all space, it's positive homogeneous. It's subadditive. Then if x, it's less or equal than 0, then P of x, it's less or equal than 0. And finally, And finally, that L P of x, it's equal to L of x for x in y. So let me prove these 4 claims. So that it's positive homogeneous, we have to show that if A it's positive, P A of x, it's equal to A P of x. Right? This proof it's very similar to the other ones. So P of AX is the infimum over all Ly for y in y and x A less or equal than y. So now let me consider that set. Since A is strictly positive, I can divide it by A. I can divide it by A and multiply by A. So A, it's a constant, so A times this set, it's equal to A times this set. Therefore, y in y and y divided by A in y is the same thing. So this set corresponds to the set of all Lz. If I call z y divided by A, what I claim is that this set here corresponds to the set of all z in y such that x is less or equal than z. So this set corresponds to that set. There is a one-to-one correspondence between these elements. Therefore, since I have an inf A, this is equal to A times the infimum, but this is P of x. So PAX it's equal to APX, which proves that P is positive homogeneous. Right? Well, I hope you're convinced that these two sets are equal. Now let's prove that P is subadditive, and well, the proof is also similar to a proof which I presented in the previous lecture. We have 2 points, let's say Z1 and Z2, and we have to show that P of Z1 plus Z2 is less or equal than P Z1 plus P Z2. Fine, so let's fix epsilon, positive. Since P Z1 and P Z2 are finite, we can always find a y which is bounded below by Z1 and whose value of L of y it's almost equal to the infimum. So there exists y1 in y, y1 larger than Z1, and L of y1 it's less or equal than P of Z1 plus epsilon. Okay. This infimum is finite, so we can find one point which almost reach the infimum. And the same thing for y2. So there exists a y2 in y, y2 larger than z2, and L of y2 bounded by less or equal than P z2 plus epsilon. So L of y2 almost attains the infimum, doesn't attain by epsilon. So y it's a linear space. So now if I consider the element y1 plus y2, this is an element of y. y1 plus y2 it's larger than z1 plus z2. Therefore, P of z1 plus z2, which is the infimum, it's less or equal than L of y1 plus y2. But L of y1 plus y2, it's bounded by these two quantities. So this is bounded by Pz1 plus Pz2 plus 2 epsilon. And therefore, we prove that P of z1 plus z2, it's bounded by P of z1 plus P of z2 plus 2 epsilon. This holds for all epsilon. We can send epsilon to 0 in order to get that P is indeed subadditive. Now, let me prove that if x is less or equal than 0, then p of x is less or equal than 0. So let's assume that x is less or equal than 0. I want to prove that p of x is less or equal than 0. Well, but 0 certainly belongs to y. And x, it's less or equal than 0. L of 0 is 0. So this means that the infimum, which is p of x is the infimum. Since 0 belongs to this set, this infimum is less or equal than L of 0. And since L is linear, L of 0 is 0, which means that p of x is less or equal than 0. So that's easy. And finally, let's show that on the set y, p of x is equal to L of x. So p of x, so let's take x in y. P of x is the infimum of L of y such that x is less or equal than y in y. Well, to prove that these two are equal, let me first show that p of x is less or equal than, so I want to show that this infimum is equal to L of x. So let me first show that p of x is less or equal, but that's clear because since x belongs to y, x is an element of this set, and therefore p of x is smaller because it's the infimum than L of x. So this inequality is clear. So now let's prove that L of x is less or equal than p of x. And to prove this inequality, well, I just have to show that L of x is less than L of y for all y in y, such that x is less or equal than y. Okay, if I can show that L of x is less than L of y for all y bounded below by x, then L of x will also be bounded by the infimum, which is p of x. But that's clear because L is monotone. We've seen that L is positive and therefore monotone. Since y of it's larger than x, L of y it's larger than L of x because x it's defined, x belongs to y, therefore it's defined. And therefore this inequality follows from that inequality and the monotonicity of L. So we prove these four properties of our function p. Now we can use the Hamilton-Jacobi. We have constructed this function p, which is positive homogeneous and which is subadditive. On the other hand, we claim that L of y is bounded by p of y for all y in y. Well, this follows from this property. Actually, we proved the identity on y. So L and p coincide on y. So in particular, L of y is bounded by p of y. So the two conditions on in the Hanh-Banach theorem are satisfied. So we can use the Hanh-Banach theorem to say that we can extend the linear functional L to all space. So there exists a functional L, which is defined on B of omega to R, which is an extension. So L of y it's equal to L of y for all y in y. And now what remains to be proven is that L is positive. So let's take x non-negative. Well, the property we are going to use here is that, well, if x is negative, then p of x is negative. So let's take x positive. Well, if you multiply by minus, you get a negative functional, now you know that L, the Hanh-Banach theorem, tells me that L of x, it's bounded by P of x for all x in B of omega. So, well, I know that minus x, it's negative. That's fine. But what the Hanh-Banach extension tells me that L minus x, it's bounded by P minus x. P minus x, so let me multiply that by minus 1. This tells me that L, which is linear, x, it's larger than minus P of minus x. Now, P of minus x, well, this is negative, so P of minus x, it's negative, but with the minus sign, this is positive. And so that we get that L of x, it's non-negative. So let me just repeat that. Maybe it wasn't clear. I have the Hanh-Banach theorem tells me that there is an extension, so there is a linear functional capital L defined on the whole space, which is an extension, so it coincides with L on Y, and also L, it's bounded by P on the whole space. So I know that for Lx, it's bounded by Px for all x. Fine. So now I want to show that L is positive. So take a function x, which is strictly, well, it's not negative. This means that minus x is negative. Now apply this inequality to minus x. So I know that L of minus x, it's bounded by P of minus x. Multiply, well, by linearity, this is minus L of x. Multiply that by minus 1 to get that L of x, it's greater or equal than minus P of minus x. Now, minus x, it's negative. And we know that if a function is negative, then P of it, it's negative. So minus P of minus x, it's negative, which means that minus P of minus x, it's positive. And from that, we conclude that L of x is positive, which means that L is positive, and that completes the proof of this theorem and this lecture.